Hello everyone, welcome to Stochastic Calculus for Finance 1. This is section 5.2 on the first passage of time, and we're on the fourth and final part on this section. So in our previous video, we gave the definition of passage of time and we proved these first two properties. So now we're going to focus on the third one here. And to understand better what this means is what this third property is telling us, let's just have a quick graph here and just look at it. So this is time, and time, we have time t1, time 2, time t3, etc. And we might have many different levels here. But notice here we're talking about tau1, the stopping time. We're stopping time at level 1, right? So that means this is the level that we're interested in. And we're saying like, okay, so we want to know what is the probability that the first time we reach level 1 is at t equal to 1. What is this probability? Well, that probability is given basically by this formula given here, where P is the probability of getting head, or actually the probability of moving up, and Q is the probability of getting tail, or if you want to think about it, is the probability of moving down. And this is true for symmetric random walk, but in more general terms, it's true for just the random walk stochastic process. And that's what we want to be able to show going forward. So I'm putting this on the left side, on the right side here. So as usual, so we can remember exactly what we're trying to do. So now, we have seen this theorem, right? This theorem 5.2.3, and from this, thanks to this theorem, we have shown that actually this expression here is true. And if we just take m is equal to 1, then we have this expression here, and that we're saying is true. And so now what we're going to do is we're going to work with, like, on each side of the equation. We're going to work with the left side first, and based on the definition, we're going to come up with something, and then we're going to work with some the right side. We're going to do some mathematics to come with an expression, and then later, by simply equating these two and looking, we're going to find, okay, we have something that will help us really come up to this. So enough talk, and let's get to it. So now we're focusing on the right side first, on this guy, on the left side, sorry. So, well, we have the expectation of the function of a random variable. So basically the value of the expectation is just given by this, right? We just take the probability of each of the possible events, and then we multiply by the function of random variable at that event. When the random variable take that value. And that's what we do here. So if tau1 is equal to 2, then we need to multiply by alpha to the power 2. If tau1 is 3, then we just need to multiply by alpha to the power 3, right? Which is just the function of the random variable. So nothing too mysterious here. And now here we can notice something interesting. Well, let me show you that first. So we're saying, like, basically that the symmetric random walk can reach level 1 only in odd numbers of steps. So why is that? Well, if you don't believe that, then let's say, okay, well, let's try to reach the level 2 in an odd number in an even number of steps. So let's say level 1 in an even number of steps. So let's say, for example, this is level 1. This is the level we want to reach, and our goal is to reach this level at only after 2 steps. So we want to reach level 1 by flipping the coin twice, or by moving to two steps into the random walk. Well, let's see how we can do that. So let's say, for example, we flip the coin first, and we get a head, right? So we start the random walk starts at 0, and when we get ahead, we move up by 1. So then you can see we already failed, because what we want to do, we want to reach level 1 for the very first time at time t2. But then by getting ahead and moving up, we already at level 1. So this is already a failure, and so you can go to the second step and flip. If you get a head or you get a tail, whichever you get, I don't care, because just by getting the head is bringing us up at level 1 already, and we failed. Okay, so then let's try something else. Let's say like we flip the coin first and then we get a tail. What happens? Well, if you flip the coin and we get a tail first, then we're gonna go down by 1, right? So we'll be here. So then from here, two things can happen. We can flip the coin and get a head, well, in which case we'll be moving up by 1. So if we move up by 1, then we'll be at level 0. So again here, we are at time 2, but at time 2 we are not able to reach level 1. We are only able to reach 0. So then we failed. So this path also doesn't work for us. So what if we get a second tail? Then here obviously we just go down again, and at time 2 we can clearly see that we haven't reached this level 1 that we want to reach at time t equal to 2. So that's impossible. We were not able to. No matter what we do, we can't get there. So the probability of reaching here after 2 time steps is 0. How about 3 steps? Can we reach level 1 for the very first time at t equal to 3? Well, it's very possible, right? Let's say you flip the coin, you get a tail. So you're here, you come down by 1, and then you flip the coin again, and you get a head, and then a head. Then you're moving by 1, and by 1 again, and you will be at level 3. Right? So you'll be here, and then you'll be here. That's all. So then you will be successful. So that means we can reach it in odd number of steps, but you cannot reach it in just even number of steps. And that's what we're saying here. And because of that, then we can replace all the probabilities where we're having like where the time is something that's even by 0. And hence we can even simplify further by this 2j minus 1. So now it's very clear to us like where this weird thing is coming from. This is just because we're caring here only about the odd number of steps. Because 2j minus 1, no matter what you do, 2 times j, if j is an integer, then that's going to be an even number, and then minus 1, you're going to get to an odd number. Nothing too deep there. So with that, then we can make a note of this. We put it on the side as well, because this is something that we'll be using later. And then we can move to the second part of our proof. So now we're gonna work with the green part right here. So that's the right side of the equation. So if you notice what we have up here, this we can replace by we can just think about this as a function of like f of x is equal to 1 minus square root of 1 minus x, right? And then we see that essentially this expression here is going to be equivalent to this. And what we can do from here is we can basically take the Taylor expansion of this function f of x. And if you don't want to know what Taylor expansion or Taylor series are, that's the calculus concept. It's a little bit like unrelated to what we're doing here. But there are tons of resources online, YouTube or everywhere to really see, get a reminder of what this Taylor expansion is. But in brief, anyway, after you do Taylor expansion, you're gonna be noticing that the function f is going to be given by this expression you have right here. And so that means that we can essentially take the whole green part can be replaced by this expression. And if you want to, let's go in details to see where this is coming from. So so we said this is basically f alpha squared. So this x, we're going to replace this x by alpha squared. So we're going to get alpha squared to the power j, right? So to the power j, you get like the alpha 2j. And then notice that we're dividing everything by alpha as well. So by dividing by alpha, what we end up getting is alpha 2j minus 1. And that's where this alpha 2j minus 1 is coming from. And then everything else is just copy. All right. So we take that to our side again. And now what we're going to do is we're just going to equate both sides. So we know these two are equal. So these two must be equal also. Right? And because these two are equal, and we see that we're getting the exact same expression both sides here, this alpha 2j minus 1. So we can just basically ignore those. And that means like these two terms here must be equal. right? So that's what we did. So we're just focusing on now these terms here. And if you notice, what we did here is this two. Okay, this a, let's say we have a 2j minus 1. This is simply equal to a j times a j minus 1, right? Because if you just take the sum of these three, you will get the 2j minus 1, which is so it's very basic properties. I don't think I need to dig deep into that, but that's essentially what we did here. So if you can see here, you have a special case for the symmetric random walk. The random walk is symmetric because the probability of getting head or the probability of moving up is equal to the probability of going down, right? And then that means you see that you have this property here. Exactly that's what we are managed to show here. So this is true for symmetric random walk, but in more general case, it's true for even an asymmetric random walk. And that's what the so that's essentially we essentially done. That was like the third property here, and actually in the book, this third property is nothing but what we have as theorem 5.2.5. All right, thank you everyone for watching, and please subscribe and stay safe during these crazy coronavirus times. Take care. Bye bye.